Started talking about chemical equilibrium, and a reminder that chemical equilibrium involves really reversible reactions. So as we talked about, these again are reactions where you typically do see the arrows heading in both directions, and there is again a forward direction, which is our reactants that it goes to products. And as we talked about, pretty much at the sort of the beginning of the reaction, if you really don't have any products to start with, it's going to pretty much all be the forward direction that's happening. So our reactants are going to come together. As we talked about, there's several things that are necessary for products to be formed. You do need to have collisions to occur. You do need to have collisions occur in sort of the right orientation, and also with the right amount of energy. We talked about activation energy, I think, last time as well, which is that minimum amount of energy that's required for a reaction to take place. So again, just because things do collide, reactants do collide, doesn't necessarily mean that you will make products. They do pretty much need those two things. Then they do need to hit each other sort of in the correct location, and also have sufficient amount of energy really to kind of get up and over the hill to the other side. So with the correct proportion of molecules that are able to do that, they will start to obviously make some products. So we will see at the beginning, typically in these type of reactions, the product's reactant concentration starting to increase as we start to make some products. Obviously, to do so, we would expect our reactant concentrations to come down. At some point, there will be sort of sufficient amount of products that have been made. And what will happen is really the reverse reaction will sort of kick into place. And that is when those products will then recombine and go back the other way and make more reactants. And at that point, we will have sort of a continual process of reactants going to products, products going to reactants, until what is reached is what is referred to as chemical equilibrium. And as we talked about last time, chemical equilibrium, again, does not mean that you have the same amount of everybody on both sides. What it actually is referring to is the rate of the forward reaction will equal the rate of the reverse reaction. So when chemical equilibrium is reached, it's actually the rate, how fast the forward reaction is going. It will basically be as fast as the reverse reaction will be going. So the rate of the forward reaction will equal the rate of reverse reaction. The sort of consequence of that is pretty much wherever anybody was in terms of their concentrations at that point, and again, even pressures, if you were sort of dealing with pressures, they pretty much will lock themselves into place. So there really won't be a major change that will happen in their concentrations at that point when chemical equilibrium has been reached. And that is because just as quick as it breaks down to products, those products will basically recombine and make the reactants. So again, it just locks everybody into place as to where they were at that particular point. Now, there is an expression that was referred to as the equilibrium constant. And the equilibrium constant is capital K. And it is basically calculated by taking the concentration of the products divided by the concentration of the reactants. There are a couple of things, as we talked about, that's important when you do write the K expression. So if you have a generic sort of formula or reaction like this, the K in this case would be the concentration of C to the coefficient times concentration of D to its coefficient divided by the concentration of A to its coefficient and B to its coefficient. So when we do write the equilibrium expression, we do take the coefficients of the balanced equation into account. They become the exponents of each of those. Also a reminder that the brackets mean concentration, and that usually is molarity, which is our moles per liter in most cases, is basically what that little bracket basically means. This K value does tell us some information about a reaction and what happens when it does reach equilibrium. If we have a large value of K, that means that when we reach equilibrium, we should mainly have products. Again, just mathematically speaking, to get a large number, you would need more products up on top divided by a smaller number on the bottom, and that would get you more products. If you have a small value of K, that means when you reach equilibrium, you would have more reactants. Same idea. To get a small value, you would need a larger amount of our denominator there to end up with a smaller number. What is a large value? As we talked about, sort of a large value is basically anything over 1 is considered large. Anything less than 1 is considered a small value of K. K is one of the few things in chemistry where there usually are no units, so unitless. It is really just a number. And again, you can use that number to determine at equilibrium, basically what you should expect to be there. As we talked about, when you do reach equilibrium and the equilibrium constant calculations, it is a constant value as long as you do not change the temperature. So if you keep the temperature constant, say 25 degrees, and you did a bunch of different types of reactions, like you started with all reactants, you started with some reactants, some products, you started with all products, whatever it may be, it will always come to rest at the same ratio of products to reactants, and the equilibrium constant will be the same. So again, as we talked about last time, sometimes people have a hard understanding of that idea that, you know, it's like, I think it should be different because I started with more this in this reaction than I did in the other reaction, but it will always come out the same in terms of the proportion of products to reactants, as long as you not change the temperature, the value of the equilibrium constant. And when we talk about the temperature affecting the value of K, what we're talking about, for example, is if you had a value of K at 25 degrees, that K would be different than the value of K at, say, 40 degrees Celsius. All at 40 degrees Celsius and did a bunch of reactions, all the K values should be the same. If you kept it all at 25 degrees Celsius and did a bunch of reactions, the K values should all be the same. But if you were to compare 25 to 40 degrees in terms of the K values, they would be different values because the temperature is different. Any questions on that there? Now, obviously, this is an equilibrium constant, which means if you had to do any of these type of calculations here to figure out what K is or any of those things, you would need to, do you have the equal concentrations to put in there to do so. There are also a couple of things that we do not include when we calculate K. So when we do the K expression, really the only things that are put in there are things that are aqueous and gas. We do not include anything that is solid or a pure liquid. So these guys here, solid and pure liquid, do not get included into the K expression. Anything that is aqueous and a gas does get included into the questions on the end of there. Okay, so we'll pick up really where we kind of left off. We left off talking about Le Chatelier's principle. Le Chatelier's principle is the idea of, as we talked about, you have basically a system that's at equilibrium. And basically, when the system's at equilibrium, you basically add some type of stress to it. And remember that what we talked about in terms of stresses, it could be something to do with the concentration. It could do something to do with the pressure or volume. It could do something with the temperature. It could do something with a catalyst as well. So these are all basically stresses that you could do to a system. We did an experiment the other day where we really focused in on concentration, and we talked about it last time. So let's review again what will happen. When you do add a stress to a system, what will happen is basically the equilibrium will be disturbed. And what will happen is the reaction will want to get itself back to really that equilibrium situation where the rate of the forward reaction and the reverse reaction will equal each other. So typically what happens is one of three things. in order to get back to equilibrium, usually the reaction will either shift to the right, which again means that it's going to make more products. It may shift to the left, which means it will make more reactants. And there can be situations where, even though you sort of added a stress to the system, based on how the system is sort of set up, there really will be no change that will occur. So it is possible that, even though you might do something to it, it really won't cause an overall change to occur. But in a lot of cases, it will do one of those two things. Either it will shift to the left, shift to the right, and again, occasionally no change. So we talked about concentration last time, and again, concentration, there's basically two things that you could do, kind of like what you did in the lab. You could either add more, and when we do add more concentration, basically what we expect to happen is it will shift away from the side you added it to. So basically what that means is if you add more reactants, we would expect more products to start to be made. So it would shift away from the reactant side. And if you added more products, we would expect it to shift away from the product side and make more reactants. Really, the reason why that occurs is if they're quicker, and that will kick off the forward direction of that reaction to take place. Opposite is true if you added more products, say on this side of the arrow. What that's going to do is allow more reverse reaction to occur. So A is a good way to remember that. You add away. As we saw in the experiment, you could add more by simply just taking a reagent bottle and dumping it into the beaker, something that's in the equation. The way that we remove something, like we talked about, is really two ways to remove something. You could either add something that will react with something in the reaction to make a solid, which then is like reaching in there and kind of pulling it out. Or you could add something that makes water, which is another very common way that you could remove something. And those are in reactions where there's OH minus or H plus involved. So when we do remove concentration, it will shift towards the side that we removed it. So if we remove some reactants, it will shift towards the side of the reactants. If we remove products, it will shift towards the side of the products. You can think of it like if you, kind of remove some reactants, there's kind of a hole on that side. So to fill that side, it's going to kind of shift towards it. You again would have more products at that point that will be able to react with one another and kick the reverse reaction to take place. Same thing if you remove some products. Once again, you kind of have a hole on that side and more reactants in this case, and that would cause the forward direction to occur to kind of fill the hole, if you want to think about it that way. So when we do remove, again, it always goes towards whichever side that you remove. So clearly, when we look at a beaker or test tubes like you did yesterday, there really is no like left side of the test tube, right side of the test tube. So when we obviously talk about left or right, we're talking about the overall reaction and, what are reactants, what are products. Because in a reversible reaction like this, you got everybody kind of floating around in the solution. You got reactants, you got products, you got everybody kind of floating around together in there. Any questions on that there? So then let's talk about another aspect of the Chatleir's principle, which is pressure and volume. And a lot of times these guys are sort of tied together, and a lot of times it really does involve sort of a gas situation here where gases are involved. And when we think about gases, we think about pressure, volume. We should think about our friend, perhaps Boyle's law, which is P1 V1 equals P2 V2. But more importantly, when we increase the pressure, that means that the volume will decrease, right? So they go opposite of each other. So what happens is either you increase the pressure or you decrease the volume, all which is going to put all of our gas molecules pretty much close to one another. And that's really why we do see a rise, obviously, in the pressure. So the effect that's happening here is the pressure is going up. So really, to sort of bring the pressure back down in the smaller volume, we would need less gas molecules. So it will shift to whichever side has the least number of gas molecules, because basically we lowered the volume, the pressure went up. So to bring the pressure back down, we need less gas molecules in that smaller volume. So small volume, less gas molecules. How we figure that out is very simple. We just look at the equation. Everybody's got G's next to them, right? Or gases, and you count the coefficients. So there's 3 on this side, 2 on this side. It will shift to whichever side it needs to shift. So there is no left or right in this case. It really is reaction dependent as to which side has the least number of gas molecules and which side has the most. Opposite is true. If we decrease the pressure, that usually means that our volume gets larger. So we start to see an increase in the volume here. It's going to have a lot more room for everybody to fly around in. And what we're seeing is the pressure coming back down. So to kind of fix that change, to bring the pressure back up, we would actually need more gas molecules. So it will shift to the side with more gas molecules. And again, it is dependent, obviously, on the equation that you're looking at as to which side has more or which side has less. So in terms of volume, so molecules, large volume, more gas molecules. That's a good way to kind of remember, kind of which one of that is. Any questions on pressure and volume? So if we had something like 2A plus 3B goes to 4C, and let's say that we added more A, we removed C, we increased the pressure. So what will happen in each of these cases will shift to the left, to the right, or no change. So take a moment and think about what will happen in each of these cases here. Reactants, that means there's going to be a lot more reactants available to react, and it's going to kick off really the forward direction. So we should expect it to shift to the right in this case. Again, just the greater availability of our reactants should allow that forward reaction to really take place. If we remove C, C is over here. So when we remove, it really goes towards the side we removed it from. So if we get rid of some C, we once again will have kind of an abundance of reactants present. And that is going to basically also cause a reaction to shift to the right to kind of fill the hole we made there by removing C. So we would expect it to shift to the right here. Any question on those two? Now, if we increase the pressure of this system, that means that really our volume should go down. And when our volume goes down, we then have a much smaller volume. So the sort of change that occurs as the pressure is going up, we want to bring the pressure back down. We now have a much smaller volume. So small volume means we need less gas molecules present. And in this case, if we count up our gas molecules on our reactant side, that is 2 and 3, that is 5. On our product side, that is 4. So in this case, it would shift to the right as well, which is the side that has the least number of gas molecules. Yeah. Yeah, so in the case where you adjust either one or two things in sort of a gas situation, you adjust either the volume or the pressure, which are sort of tied to each other through Boyle's law. As one goes up, the other goes down. It will always shift, if it's smaller volume to the side that has the least number of gas molecules or the side that has the most. And how to count them is just simply the coefficients. They do have to all, obviously, and you would only count the ones that have G's. You could have some in there that are not gases, so you wouldn't obviously count those. You would just count whichever ones are gas molecules on each side, and you can use the moles as the coefficients because those are moles of each of those. There's also how many molecules of each of those there are as well, if you remember from stoichiometry. So that's just a really quick way just to count the coefficients. Other questions? The next thing we're going to talk about in terms of Le Chatelier's principle is temperature. Temperature works the same way as concentration. So it works the same as concentration, which means that if we increase the temperature, it will shift away. And if we decrease the temperature, it will shift towards it. So how do we know which way is away and which way is towards it? It really depends on the type of reaction that you're dealing with, whether or not it's an exothermic reaction or an endothermic reaction. So a reminder that an exothermic reaction means that heated energy is released. And what that means in terms of a reaction is we sort of think of heat and energy, although it may not be correct in all aspects, as a product in that case, like it's being given off. So we think of heat and energy as really a product, which means if the reaction is increase the temperature, it should shift to the left. And if it is exothermic, you decrease the temperature, put everybody on ice, it should shift to the right. Now, there are other ways and more common ways that sort of exothermic or endothermic is basically told to you in terms of a reaction. In most cases, people will use the delta H, which we talked about earlier on, which is the enthalpy of a reaction. And a reminder that if the delta H is negative, that is a exothermic reaction. So remember, any heat value, energy value that's negative is basically exothermic. It would be true. Any heat or energy value that is positive would be an endothermic reaction. So in an endothermic reaction, heat and energy is absorbed. And in terms of a reaction, we consider it a reactant in this case. So we really kind of consider heat and energy as a reactant. And again, as I mentioned a second ago, the delta H would be a positive value. So remember, actually, it doesn't really matter at all the number that's associated with the energy value. If it's a positive number, it's endothermic. If it's a negative number, it's exothermic. That's really all you need. So it's a little bit off for an endothermic reaction. If we increase the temperature in an endothermic reaction, it would be like adding more reactants. So actually would make more products, so it would shift away. If we put it on ice, it would actually remove the heat and energy or reactants, and it would cause it to shift towards it. Questions on that there? The sort of last thing is if we add something like a catalyst, and as we talked about earlier, a catalyst, again, is typically there to speed up a chemical reaction. Again, it is not a reactant, and it is not a product, and it does not get used up in the reaction. It is really there to simply sort of facilitate the reaction, in most cases occurring faster. It actually will have no change on the equilibrium. So have no change on the equilibrium. You will just get there quicker, but it will not cause it to shift to the left or shift to the right. Cause no changes as well. It's got some type of gas situation. Maybe you add something like a noble gas to it. So you add something like a group 8 gas to it. Will also cause sort of a no change situation basically to occur. Any questions on that there? All right, so let's see. So we got 2A. I'll say the delta H is, I'll say 125 kilojoules. All right, so will these things cause it to shift to the left, to the right, or no change? Let's see here. Let's say we increase the volume, we decrease the temperature, we added more B, we removed A, we added a catalyst, and let's see here, let's see, we had more B. Now let's say we added some C. And let's just say we then increase the pressure. All right, so for each of these cases, we'll go to the right, we'll go to the left. Will nothing happen? So increasing the volume means more space. That also means that we would see the pressure start to come down. So to fix that, to bring it back up in that bigger volume, we would actually need more gas molecules to fill it. So in this case, looking at this equation, there's 2 here and 1 here, which is 3 on this side. In this case, there is 5 gas molecules. So in this case, we would expect it to shift to more gas molecules. Again, a good way to remember that, larger volume, more gas molecules to kind of fill it is a good way to do that. Any questions on that there? Here with B, adding more B, which is a reactant, will cause more reactants to be available, and that would cause the forward direction to occur. And that would mean it would shift away from it, which means it also would shift to the right-hand side. Adding a catalyst will cause no change to occur. Again, you will just get there faster. By the way, catalysts are sometimes written on top of the arrow, is oftentimes where they do kind of write those in equations. Decreasing the temperature. So decreasing the temperature, we do need to decide, is this reaction exothermic or endothermic? In this case, it is which one? This reaction is endothermic, as we have a positive value here. So this is endothermic, which means if we were to actually put the heat and energy into the equation, we could think of it like a reactant. So in this case, we're going to decrease the amount of heat and energy, and that is like removing reactants, which means it should cause it to shift towards the side we removed it. So it would go in this case towards the reactant side. Any question on that one there? Yeah. No, so the positive just tells us what type of reaction is. Is it endothermic or exothermic? So the positive value means that the reaction is endothermic. And the way we treat endothermic is like it's being absorbed. So we think of heat and energy as a reactant. So that's why we put it on the reactant side. So what makes it sort of shift that way is actually what we're doing, which is decreasing the temperature. And that would be like removing more reactants. So you want to use your like delta H value there, positive or negative, to determine is it exothermic or endothermic. And then what you could do is just kind of put heat or energy on one side or the other. And then basically it just follows the same thing as concentration. So if we remove it or lower the temperature, it will go towards the side that has the heat or energy. Or if you increase the temperature, it would go away from the side that had the energy. Other questions on that? Here we're going to remove A, which is a reactant. So it's like creating a hole on that side. Also, it means we have more products in this case. All that's going to do is kick off the reverse reaction to occur. And we would expect it to shift towards the side we removed from. And lastly here, no, not lastly, we're going to add C. So adding C will do exactly what I just said. Definitely increase the reverse reaction. So it will cause it to shift away from adding it. Lastly, here, we're going to increase the pressure, which means in terms of the volume, it should come down. So in this case, we have a smaller volume. So in a smaller volume, we want less gas molecules. And in this case, we calculated it earlier on the left-hand side there, or the reactant side has only 3 gas molecules versus 5 on the other side. Any questions on any of those there? Okay, so here we'll just go through these. These are ones we just talked about. So again, when a reactant or product is added, it will always go away. And when we remove it, it always goes towards it. Again, in terms of gases, smaller volumes need less gas molecules, larger volumes need more gas molecules. And again, opposite of the volume is the pressure. So again, if you have a large volume, smaller pressure, smaller volume, large pressure is the way to look at that. Remember, temperature is really based on exothermic and endothermic, and that's really what you want to determine, based on your reaction, which type of reaction it was. Now, also with temperature, as we talked about, it is, again, the one thing that will change the actual value of the equilibrium constant. Again, if you change the temperature, if you keep temperature constant, it will not go one way or the other. So let's see here, go through this one since we got the answer and see how many of the following changes would lead to a shift in the equilibrium position towards the reactants. So let's go through the first one. If we remove CO, which is over here, removing means it should shift towards it. So that definitely would not make more reactants, right? So that one's not going to do it. If we add O2, which is here, that would be adding more products, which should kick off the reverse reaction. So that would make more reactants. If we remove CO2, once again, it's like making a hole there on the left-hand side. And to fill it, the reverse reaction will kick off because there's more products. So that guy would do it. And if we increase the pressure in this by decreasing the volume, so once again, we have a smaller volume, so we want less gas molecules in that smaller volume. Here we have 2 on the left-hand side, and taking both of these together, which are gases, a 2 and a 1 for the coefficients is 3. So that would shift it to the left-hand side there. So that guy would do it. So it is those 3 guys there that would cause everybody to shift to the reactant side. Any questions on that there? All right. So in this case, we want to know which of the following would decrease the amount of H2. So since H2 is a product, the only way to decrease the amount of H2 is to cause the equilibrium to shift away from it, right? So we'd want to shift it away. So let's see if the first thing does it. Water being added. In this case, water is a reactant, which would cause it to shift to the right, which means we would actually get more H2 formed. By the way, water here will affect the equilibrium because why? Water is in which state here? It is in the gas state, so it will affect the equilibrium. Water in the pure liquid state will not affected. So, just because it's water, it happens here to be a gas, which means it will participate in the equilibrium. So it does affect it here. Again, water in the liquid state would not. The volume of the container is doubled. So we're increasing the volume. That means that we should have more volume. We need more gas molecules. Left-hand side here is 2. Right-hand side is 4, I think. So we need more gas molecules. In this case, would shift it to the right, which would not be good because then that would make more H2. So that is not going to work. CH4 is removed. So CH4 is over here on our reactant side. That means there's kind of a hole there. So the equilibrium would shift towards it. And that would cause our H2 to start to decrease, right? Because we're making more reactants. So that would do it. So I'm assuming this last one would not do it. The temperatures increase in the reaction vessel. In this case, it is endothermic, which means heat is a reactant. And increasing the heat would cause it to shift away. And that would make more products and more H2. So that would not do it. So in this case, it is number 3. That is actually the thing that will cause the shift the correct way based on the question. Any questions on that there? Now, there is a way, for example, if we had, say, something, bless you. Let's say we had something like 2A plus B goes to 3C. Let's say I decrease the volume in this case, and all these guys are gas molecules. My bad, G's there. They're all gas molecules. Which way would it shift in this case? If I decrease the gas volume, right? That means I want more or less gas molecules. Do you want less? So on the left-hand side, how many are there? There are 3, 2 here and 1 here, right? Right-hand side, there are, they call that a tie. Yes, there is no side with less or more. So this is a situation where this would be a no change situation. So that can occur, obviously, like we see here. You may end up with the same number of gas molecules on both sides. So it won't shift either way because it's basically the same as where it's starting at that point. Yeah. Any questions on that there? Any questions on Le Chatelier's principle? Also, if you think about sort of temperature and stuff like that, figure out, is a reaction exothermic or endothermic by your observations, like an experiment we did the other day, like this guy here, plus a little thiocyanate, making our FeSCN2+, right? This guy is sort of a blood red, right? And this guy is more of a, was like a yellow, orangey type color. So let's say I increase the temperature, basically put all my test tubes in a hot water bath, and it turned yellow. Then I put all my test tubes in a ice bath, right? Kind of lowered the temperature. It turned red. Is this reaction exothermic or endothermic? So let's think about what each of these means. When I increase the temperature, that's like adding energy, right? Which means it should shift away. So shifting away means in this case, I saw it turn yellow. So shifting away would mean my heat would have to be on the product side to do that, right? My other observation should also agree. I lowered the temperature, which means it would be like removing it, which would cause it to turn red and shift to the right, which means my heat would also have to be on the right-hand side. And this would be an exothermic reaction in here. So like those experiments we did before, you could throw your test tubes on some ice, throw your test tubes in some hot water, and based on the colors, if you do have colors on each side, you could basically experimentally figure out whether or not a reaction is exothermic or endothermic based on what colors you kind of see happen when you kind of put them into those environments. Any questions on that there? Yeah. So as we talked about as well, the value of K, which is just a number, means that, we have a large value over 1. We should mainly have products when we reach equilibrium. And as I think we talked about last time, there are some various degrees of large values. You could have an equilibrium constant of like 1, or you could have an equilibrium constant of like times 10 to the 30. If you have a super large value of K, even though essentially it is a reversible reaction, it is almost like a one-way street. It's all going to go to the product side. But even a reaction like that, if you had a really large value of K, where essentially everything is going to go to the product side, it is still a reversible reaction. So you would still have just a smidge of those products coming back the other way. But for the most part, everybody is heading to the product side. And the same thing would happen if you had sort of a small value of K, got a really small value of K, like to the minus 36 times 10 to the minus 36. Again, in a situation like that, it pretty much means you have all reactants. Not much of it is going to the product side, but it is still a reversible reaction. So there is still a little bit of it kind of breaking apart on the product side and stuff like that. So there are various degrees of K, and sometimes we sort of assume in a lot of cases or some cases that even though it is a reversible reaction, you know, it's pretty much all kind of going one way or the other, depending on sort of the value. Calculated from known set of equilibrium concentrations. Unknown equilibrium concentrations can be calculated if the value of K and the remaining equilibrium concentrations are known. So you can calculate equilibrium concentrations. If you know the value of K and you know some of the other equilibrium concentrations, you could obviously just plug and chug into an equation. So for example, here, if the equilibrium lies to the right, that means product a large value of Q. So if it lies to the left, we would have a small value of K, or mainly reactants present at that point. So here's an example of that. In this reaction here, H2 plus I2 goes to 2I. Calculate the equilibrium concentration of H2, given that these are the equilibrium concentrations of these guys. And we do have the K value of 50 given to us. So we would start here by writing our equilibrium expression, which is our products. And we would square it because of the coefficient that is there. We would divide it by our reactants, which is H2 and I2. Again, each of the coefficients here are 1, and that would equal 50. In this particular case, we do have HI given to us. So we have 5 times 10 to the minus 1, and we do square it, divided by H2, which is what we're looking for, and our I2 concentration of 1.5 times 10 to the minus 2 equals 50. We would basically multiply everything on the bottom to the other side. So we would end up with, if we did it like it shows down there, if we get my calculator to work, thank you. So we have 5 to the minus 1 squared would give us 0.25 equals 50 times H2 times 1.5 times 10 to the minus 2. Again, just multiplying everything on the bottom to the other side. We then can bring both of these guys back over to the other side by dividing. So we can take that divided by 50 and take that divided by 1.5 to the minus 2. And that'll give us something like the H2 concentration 0.333. Since this is a concentration, we would want molarity here. And in this case, since everybody had 2 significant figures, we definitely would want 2 significant figures there on our answer. Any questions on that? So again, we're dividing 50 to both sides, and then dividing 1.5 times 10 to the minus 2 to both sides. So this is a case where you do know the equilibrium constant, and you do have some equilibrium concentrations, which will allow you to calculate a missing equilibrium concentration. First off, any questions on that? Now, you also can have a situation where you are given not equilibrium concentrations, but you are given the initial concentrations. And what you want to do is basically figure out what is the equilibrium concentrations of everybody. So what we'll do is we will steal this equation here. So let's say we do have this H2 plus I2 going to 2HI. And the K value is 50. And let's say in this reaction, we started with .5 molar H2 and 0.5 molar I2. And we want to know the equilibrium concentrations of all species that are there. So in this case, we actually have the initial concentrations And we're looking for what everybody's equilibrium concentrations are. So there is a method that we use to calculate things like this, which I will show you now how to do, and you will never see again until Chem 1B. I don't know why they do it in this class, but we will do it. So the method that we use is what's referred to as an ice table. And an ice table, the I stands for initial, C stands for change, and E stands for equilibrium. And in an ice table, there's usually an unknown, and the unknown is usually the change part. And in most cases, we use the letter X as sort of like our unknown and what we're really trying to solve for. So this is usually what we're trying to solve for, is like our unknown. So how you would sort of approach an ice table like this is you would start with the equation, and obviously you do want to make sure it's balanced. And we can write our equilibrium expression. So our equilibrium expression in this case would be our products, which would be the concentration of HI squared, just like we did on the previous slide, divided by the concentration of H2 and the concentration of I2, and that's going to equal 50 in this case. So to do our ice table, we start with the I, which is initial. So it's the initial concentrations of everybody. So for our H2, we had 0.5 molar. For I2, 0.5 molar. And in most cases, if you are not given any information about the products, it is very safe to assume that it's going to be 0 to start with for products. So it's very, in cases, maybe even more than that you're going to be starting with 0 amount of your products in this case. Now, because we really don't have products there to start with, we should expect this reaction to pretty much start out as the forward reaction, because all we have are reactants. So we should expect really this reaction to head in this direction. And that's important because as it heads in the direction there to the right, we should expect that the reactants should increase or decrease with time here. The amount of reactants should start to decrease to make our products, and our products should start to increase. So in an ice table, the way we represent something decreasing and something increasing is anything that is decreasing has like a subtract or a minus. Anything that is increasing has a plus sort of sign with it. So in the change part here, what we're going to do is we're going to go minus X. And we do need to take actually the coefficients into account here to make sure that we do get the right mole to mole relationship. Coefficient happens to be 1, so that's why it's like minus 1x basically. This would also be minus x because again the coefficient is 1. And here this would be plus 2x because the coefficient is 2. If you do not put the coefficients in with the x, you will have the wrong mole to mole relationship and you will get the wrong answer. So it kind of does all the stoichiometry part together when you do that. Any questions so far? Yeah. We're subtracting on the reactant side because we're assuming initially we have no products. So the only reaction that's going to probably happen is the forward reaction heading towards the products, which means basically in order to make products, the amount of reactants will start decreasing, which is why they're represented with a negative, and the amount of products should be increasing, which is why they're represented with a positive. Other questions? All right, we're now ready for our equilibrium line here. And our equilibrium line would be 0.5 minus x. We're just going to bring everything down. 0.5 minus x and 2x. First off, any question on the table here? The goal here is really to find x, which is the change. So to do that, what we're going to do is we're going to take our equilibrium line. So we're going to take all these guys here at equilibrium. And because they are at equilibrium, we will then put it into our equilibrium all the equilibrium lines and basically put it into our expression. And when we do that, what we will end up with here is up on top, we will have 2x squared divided by 0.5 minus x, 0.5 minus x, and that will equal 50. Yeah. At this point, it's some math time here. We want to solve for x. So this is a nice, easy one, which I would assume, which is what you would have in this class. They do get a little bit harder as you get to 1b. We're going to make a big giant square root on both sides because it looks like a perfect square. Yeah. So when I square, end up with 2x up on top. I will end up with just 1 of the 0.5 minus x. The thing I personally forget to do most of the time is actually take the square root there on the right hand side, which is 50. We will get 7.07106. At this point, what we want to do is solve for x. So we want to multiply to the other side. So we're going to multiply everything on the bottom to the other side. That will give us 2x is equal to that times 0.5 gets us 3.5355 minus 7.071. I'll just call it x. At this point, we want to combine x's, so we're going to add this guy back to the other side. When we do so, we will end up with 9.071x equals 3.5355. Obviously, now we're going to divide that to the other side. When we do, we will get an x value here of we'll call it 0.390. First off, any questions on that so far? Yeah. How did I get to 3.5? So basically, I took this entire bottom part here and I multiplied it to the other side. So I took each of those individually times 7.07 to each side down. And then that gave us what was here. And at this point, I then added the 7.07 to the other side because they were both x's. That combined the x's, and then I divided that guy to the other side. Yeah. Other questions on that? Now, the 0.390 is not necessarily the answer in this case. It is the x value for everybody that is in that table. So this x value is the x value here, it is the x value here, and it is the x value that is there. That means that we could then put that number in and solve for what the equilibrium concentrations are. So the H2 concentration at equilibrium will actually equal the I2 because it's the same. And that would be 0.5 minus 0.390. That gives us 0.5 minus 0.390, 0.110. Now for our HI at equilibrium, it is 2x. So it would be 2 times 0.390. So 2 times 0.390, 0.780. And these would be our equilibrium concentrations of everybody in this reaction. Once this reaction obviously reaches equilibrium. Question all that there. The good thing is it is math, right? Which means in case I screwed up, I could do what with those numbers I just calculated? I could put those numbers into here because those are now the equilibrium numbers. So I could take 0.78 and square it, divided by 0.11 and divided by 0.11, and it should roughly equal around 50. And it does, it's about 50 point something. So it's a good way you can actually check yourself in this calculation is once you actually calculate the equilibrium concentrations of everybody, you can put it back in to the expression, and it should, with rounding, very close to your equilibrium constant. Any questions on that there? So this is something that you will again probably see mostly in 1B, unless you have something in 1A that teaches you limiting reagents using an ice table, but usually you will not see it until 1B. Any questions on that? This is very much like the last question there in the lab we did the other day. Yes, so you do need to do an ice table and kind of solve it. I will say this is, although it may not look it, is a very simple one because you could do a perfect square. More complicated ones, you got to solve using like the quadratic formula and some bunch of other math stuff, which clearly we would not do in this class. But in future classes, you will have to do things like that. Sometimes people use successive approximation and all those really bad math things. So I would say if you see a nice table in our class, should be something like this, a nice perfect square probably on both sides. And that's probably how you would probably solve it. But just so you know, there are much more complicated ways that you can solve some of these things. Any questions on that there? All right, we will, I think, lay it up here for now. We will go